right, so this week we have your research paper presentation topics are due this Sunday. Make sure you get those in. Remember on that, reread that if you need to. There's a list of topics at the bottom. There's an other line at the bottom. So if you aren't interested in any of those on the list, I recommend Googling those if you don't understand some of the terms, which you definitely won't. But if you don't like any of them or you're not interested in any of them, that's fine. Just find something that you are interested in, whether searching the web or talking to those that you work with. Submit it as a network topic. If you have any questions, you can see me before you leave. If you're tossing a couple around, if you have no clue, I can help you out. I'll bounce some ideas around before you go tonight. So that's due by Sunday. And then also review questions for Chapter 2 and quiz. A note on the quiz for week 2, there's some fill-ins that you got to fill in. If you didn't spell exactly correct, you got it incorrect. Don't worry about that. I am going to grade those manually, so those will be corrected. And so don't worry about that. So if you forgot an S on something, not a big deal. But everything's looking good so far. You're turning in. Grades are updated as of week 2. And so, again, if you have questions on research paper presentation topic, come and see me before you leave so I can help you to nail down a topic. And somebody already mentioned, I think last week, hey, if I change my mind a couple weeks from now, can I do that? If it's something that you're really passionate about doing, definitely. But I don't recommend it up front. But if it's something you're passionate about and, say, hey, I'd really like to do it because of this, I'll let you do it probably. So, but, put some thought into it. When I know some of you have already and submitted yours already. And so, but if you have any questions or need me to give you some ideas, I can definitely do that, okay? One last thing I'll mention on research topic is some students are fearful that maybe somebody else picked that same topic. And that can happen and does happen in a class this size. But you're going, in my experience, teaching this class a number of years now, no two research papers, even of the same topic, are going to be the same, and no two presentations of the same topic are going to be the same. You're going to make it up and mix it up a little bit, come from a different angle. And so I will help you around mid-semester on helping you getting started with your research paper. Also, there will be a night mid-semester down the road that will be devoted for you to spend on your research paper. In fact, let's see, I'll forward faster a little bit. It's week 8, or week 9, I'm sorry. Week 9 is the week that we will not meet face-to-face. That week is devoted to, or that night is devoted to working on your research paper presentation. And assignments that week, I believe, is only answering what did you accomplish for research paper presentation. That's it. And watching a podcast that'll help you with your outline and get started with research. That's all you gotta do that week. So I do give you a week to just devote on so you can spend this whole time that you normally would be in this classroom studying and getting research for your research paper and gathering materials. Make sense? And I did already have a podcast out there for you to watch for that. So tonight we're going to discuss Chapter 2 on OSI, and then we'll go right into the video. We'll segue right into it. It's not that long. In fact, it is 12 minutes and 59 seconds long, around 13 minutes long. It's a really good video on how data flows when you click on a link on any website, what happens behind the scenes. What happens? You might have always wondered, how does that get from the web server in China to my computer so quickly? And how does it get there? Talks about that in the video. All right, so let me go ahead and switch over here to the chapter discussion. We're going to look at some standards this week. And talking about standards, about 3 or 4 of you asked for Network Plus certification, and I'm still gathering the latest materials. They change them every semester, so bear with me. You will be getting it in your email. So those of you that did email me already that you're interested in Network Plus certification, which is the middle road certification, I'm still working on it, but I will get it done. I'll try to get it done this weekend. But they change the study materials every semester, so I want to make sure you've got newest and greatest stuff. So we'll look at some standard organizations that make up the rules and guidelines for folks in networking. And just like every industry, they have a music industry has standards, people. My dad was a musician. I played growing up and still do play a little bit. They have their own musicians union and their own musicians guild and guidelines and procedures for everything. So it's nothing abnormal to have it for networking as well. So we'll talk about the different organizations for that. We'll look at what's called the OSI model, which if you do take the Network Plus exam, you do need to know that OSI model and be able to, there's an acronym that you can use that I share with you in the packet I give you to learn the OSI model. And then explain specific functions that belong to OSI model. So we'll also look at how the OSI model works on a network between two nodes. And then we'll end on there because we won't be able to cover anything further post to the video. So we're going to end on how things work on an OSI model network. So let's start with the standards. There is standards in networking, and what a standard basically is a documented agreement, specifications on a specific area in networking. Stipulates design and performance, and those areas could be, an example would be Wi-Fi. There's a Wi-Fi standard, right? There's a protocol for wireless standard, protocol for wired standard that we'll play with tonight and look at. And different rules and regulations for that, or standards, not really regulations, but standards. And they stipulate design and performance on a particular product or service. Standards are important in the world of networking because, as you can imagine, there's a wide variety of hardware and software out there. Okay? Steve Jobs wasn't the only one that came up with hardware. There was tons of Steve Jobs out there. Now, maybe not as big companies as Steve Jobs became in Apple, but there's hundreds and hundreds and hundreds of companies like that, creating your unique hardware, unique software to meet specific needs. Standards are important because, besides wide variety, because they ensure network design compatibility. An example, Microsoft Office or Microsoft operating system. If you're going to build a hardware device to work with Windows, you better understand the compatibility things that you need to work with Windows, the drivers that you need, the software that you need. And so there's some compatibility design standards that all software companies, software developers, hardware developers work with to where everything can kind of work together. So if you go out and buy a Linksys router, it's going to work with your Mac computer, your Linux computer, and your Windows computer because there's standards in place for that to happen. There's Wi-Fi standards for that to work. Standards also define minimal acceptance performance. Like an example would be, here's the minimum standards for a server. This is how much memory you should have, hard drive space you should have. That's a standard. Now, is it an optimal standard? No, it's just a minimal standard. And there's folks that create those standards. Also, there's many different organizations that oversee computer industry standards. If you've ever been in anything in bureaucracy or government or political, you maybe will understand what I'm getting ready to say, is that when in government or in anything that's a rule-based organization generally has another rule-based organization over that for checks and balances, which isn't a bad thing. It's just the nature of the beast. But because of that, things run very slowly. And in order for stuff to get done, it might take years to implement because you've got so many. You got to make sure everybody is on the same page. You have to make sure everybody checks off on it. And so because of that, it takes a longer time to implement like new Wi-Fi standards, new wired standards, things of that nature. Couple examples of organizations that are really popular. You might have heard of a couple of these or both of these is ANSI and IEEE. These folks set the wireless standards. ANSI sets standards applied to the type of NIC needed for networks to work in wireless. And also IEEE standards involve communication protocols. So ANSI, as it pertains to wireless, does the standards for the NIC cards. And there's different type of NIC cards, by the way, for Wi-Fi. You've got, USB NICs for Wi-Fi. You've got embedded motherboard NIC cards for Wi-Fi. Even down to USB size NIC cards, like a USB heart, USB stick type drive for NIC, wireless NIC. And then the communication protocols would be, okay, security. What type of security should this Wi-Fi have? What type of ports should it fall over and flow over? What type of security standards should we have on this? So when these hardware folks create Wi-Fi routers, they have some standards to go by. That way they know, hey, when people buy this, they're going to be able to use it. And so that's a good thing. And so network professionals' responsibility then is basically to be familiar with these groups. You might not be a part of these groups that we're talking about tonight, but it's good to know about them. There is one I will recommend, we'll talk about even more in the slides, I believe, is the IEEE. It does have a student chapter I definitely recommend you looking into. If you go to the IEEE website, which we'll look at in a second, the URL for that, it does have a student chapter that you can sign up for. And when you sign up for it, you do get some perks and privileges because you're a student, that a lot of it's free. There is some paid stuff you got to do, but most of it's free, like conferences, materials, even software. Some software is free. But they usually have 1 or 2 training events or conferences in Chicago area every year for IEEE, student chapter. And they have competitions at these chapters. And in these competitions, they actually train you on whatever the competition is. And then after they train you, you then have a competition about it. And so it might be a training on how to set up a secure Wi-Fi. And then after you get that training, you go right into competition. It might be how to set up a switch and secure that. You go through a little training how to do it, and then you go into competition. And so IEEE is very well involved in education for students, and I definitely recommend you looking into it. ANSI is American National Standards Institute. They have 1,000+ representatives from industry and government both. They determine standards for the electronics industry and other fields. They request voluntary compliance with their standards. Obtaining ANSI approval requires rigorous testing, but if you have a product that has an ANSI approval that's an electronic product, it's a pretty big stamp of approval. It's very stringent on their standards and their testing. And they do have their documents online that they call white papers. They go over these standards as well as IEEE does as well. And some of these white papers are thousands of pages in length. It's definitely one of those things you want to read on the weekends next to the fireplace. No, just kidding, you don't. But they have them. EIA, Electronic Industry Alliance, it's a trade organization represented from the U.S. electronics manufacturing firms. They set standards for its members. They help write ANSI standards, and they lobby for favorable computer electronic legislation. And so you will have some in the state legislation and also in the federal branches both, lobbying for legislation like, say, on a new Wi-Fi security standard, or maybe lobbying like recent in the news is freedom of the web, being able to not have Big Brother come in and and infiltrate everything on the internet. We should have some privacy, just being normal citizens. And just because we're, you might have heard people say, well, if you're not doing anything wrong, you have nothing to worry about. That's true. But flip side of the coin is, why should those who do day in and day out live their life the best they can, work hard, have their privacy invaded? It's no different than somebody coming in your house. There's certain things I don't want people to see. I don't want to see people watching me sleep. I don't see people watching me get ready to work in the morning. I mean, there's certain things you can take it to the nth degree, right? I have nothing to hide. Really? You have nothing to hide? Okay. I think we all have some wants of privacy, right? And so this organization deals with that as well, on normal privacy issues that the U.S. citizens, and we were given that right in the Constitution to have some privacy, and it's a right and privilege of others. We have to sometimes fight for it. So this group is lobbying for us all the time. TIA is a telecommunication industry association. They're a subgroup of the EIA, and the EIA subgroup merged with former U.S. telecommunications supplier USTSA. The focus of the TIA is the standards of information technology, wireless, satellite, fiber optics, and telephone equipment. These are the folks that actually come up with the guidelines for our cabling, our Cat5 cabling, called the TIA EIA 568B series. You'll actually see this on Cat5 cable in little black text, dotted black text. It'll be on there. It'll tell you what the series is, 568B, 568A, and it's guidelines for installing network cabling in commercial buildings like our own, like Rock Valley College, like all the businesses in Rockford in the United States have to follow this standard of installation. And the cables that are created follow this standard as well. That way there's not going to be any confusion or installation problems. IEEE, Institute of Electronical Engineers, Internationally Engineered Professional Society. The goal of this organization is to promote development and education in electrical engineering and computer science fields like you guys are in. And so they host symposiums, conferences, chapter meetings, and I'm going to actually try this semester to see if I can get a hold of the date coming up. Sometimes, most of the times in the summer, but at least get the date out for you guys to be able to go to it, and maybe be able to rent a van or something and drive it to Cumberland or something and take the L in or something like that, maybe, if we get enough students interested. But they maintain a standards board, IEEE technical papers and standards, very highly respected. The organization's headquarters in Geneva, Switzerland, collection of standards organization. They represent 162 countries. The goal of ISO is to establish international technology standards to facilitate global information exchange and barrier-free trade. And they have widespread authority. These are the organizations actually that try to get cafes and educational Wi-Fi or just free internet to educational facilities in third world countries. Example was my cousin was in Iraq for 4 or 5 tours. He worked with local schools, and he mentioned ISO as being one of the organizations helping them get internet via satellite to all the schools for the kids to have internet and the teachers to have internet to teach courses maybe that they couldn't teach otherwise because they didn't have internet prior. They do now. They can teach courses, learn, and also offer courses to their students. And ISO is one of the organizations that helped them get the satellite technology for that area, raising funds and stuff like that. So they have quite a bit of pull, and they can generate a lot of money because they know they're gathered all throughout the 162 countries. ITU, International Telecommunication Union. These are specialized United Nations. And remember, if you know your history, United Nations formed in 47, right after Israel came about again in 47, 46, 47. And the United Nations regulates international telecommunications and provides developing countries with technical expertise and equipment. They were founded in 1865 and they joined the UN in 47. They're members from 193 countries. And the focus of these guys is global telecommunication issues, worldwide internet services implementation. And so you can imagine these work closely with ISO to get internet in places, get communication in places where otherwise they wouldn't be able to. ISOC is an internet society founded in 92, a professional membership society, establishes technical internet standards. And before I forget, on the last slide, anybody heard of the Raspberry Pi computer? I'll write it on the board. I've got one. I'm trying to remember to bring it in sometime this semester. This computer was created specifically for third world implementation to get the computer in the hands of every boy and girl in third world countries. It's roughly about that size, the motherboard is. And when you buy one, initially, I'll back it up a little further. Initially, they were designed just to serve this mission, but the IT community, just blew up over it. They were like, "Wow, we want to maybe help out here," and so, okay, if you put them out to sell, we'll buy them, and then it'll help you with your mission here, which forward fast 3, 4, 5 years now. It's been 3.5 years. They've sold millions of these, and when you get in the mail, they're about $35. They started out 28, 29. Then I think they're about $35 now for the base model. The base model, you get the motherboard, and you basically have to buy everything else. If you just go buy this, just a motherboard in a box with a bubble wrap around it, and that's it. It does have some peripherals. It's got an HDMI, it's got a couple USBs. For the hard drive, it's an SD slot for an SD card. And power, you have to buy your own power supply for it. But they have these other companies that have sprouted up to support the hardware. So they have a company that you can buy a plastic case for it that fits right into it. They have companies that have sprouted up like for wireless keyboards for it. And so if you go to Radio Shack, they have whole kits right on the shelf you can buy, or you can go to newegg.com and purchase them there. Yes.
I have a friend who is currently working with a guy who races cars. He's embedding the computers in the cars to keep track of performance.
Cool. Awesome. Yeah, keep us up to date on that. That'd be awesome. Yeah, there's a lot of cool uses with it because it's so small form factor. You can do a lot with it. I did a lab last semester with the Cocoa Heads Club, which you're all invited to attend. It's the second Wednesday of every month. And initially, the Cocoa Heads Club was designed for Apple enthusiasts, but it's sprouted from that to anything tech and anything geeky. And so the members of the club present something every month. There was one month I presented on the Raspberry Pi on setting up a headless web server using an iPhone, which basically, all of us have phones that we can tether our Wi-Fi with now, right? Well, this lab showed how you could tether your Wi-Fi, set up and turn it on, plug this in, and you could actually plug this into your phone for power. That way you wouldn't even need a external power, or you could plug it in your laptop. But anyway, within about 2 minutes of starting up, it created an IP address, web server, and then everybody in the room could go to a certain website URL and begin to upload files and download files. And so it could be used for an impromptu networking, file sharing, wherever you go type thing. And it's secure because when you're done with the session, you unplug it and turn it off. And so it's only literally used during whatever little meeting sessions you use it for. So a lot of cool little uses that you could definitely use it for. But the reason I mentioned on this slide was that the group of guys that created this idea was specifically for countries that maybe never otherwise could have a computer. And so they wanted to put one in the hands of every boy and girl. So they've done a pretty good job of doing that. So recommend you Googling those guys, Googling that Raspberry Pi. A lot of different places now you can buy them. If you want to see one, you go to Radio Shack. They have a little kit already for you. You can buy. I think they're like $90 or something for the kit. Okay, on this slide here is where I ended on. ISOC, founded in '92, Professional Membership Society. They established technical internet standards. The current ISOC's concerns are, as we all know, the rapid internet growth, keeping internet accessible to all, internet security, stable internet addressing, and open standards. These are the folks that actually came up with we've had for years, IP version 4. We now have IP version 6. This is a group actually the catalyst for that, which one of the things IP version 6 does is gives us more addressing available to us. both intranet and internet. Intranet and internet, both. And so ISOC is always busy trying to keep things safer on the internet. ISOC has oversee groups. One is called the IAB, the Internet Architecture Board. They're a technical advisory group that oversees internet's design and management. And then IETF, Internet Engineering Task Force. These folks set internet system communication standards, particularly protocol operation and interaction. And anyone may submit a proposal to these guys. They have a very elaborate review, testing, and approval process. IP, you might have heard of this. We're going to talk a little bit about tonight in the video, but it stands for Internet Protocol. It's the address that identifies every computer or device, you could say today, because when people say think computer, they think their desktop or laptop, but even mobile, even your phone. So it addresses every computer in a TCP/IP-based internet with a certain IP address. And an IP, and you'll learn more again about that this semester, is made up of 4 octets. And the octets can be comprised of, in between the 4, 1, 2, 3 dots, can be comprised of zeros and ones, which is a binary. And so the IP in its rawest form is a binary system. In fact, your computer in its rawest form is a binary system. Even though you don't see it, it is all behind the scenes, is zeros and ones. And so every computer on this network and on every network, intranet, like we're on here, will have a unique IP address. And you have different types of IP addresses you can have. You can have a private IP address, which like we have in this room, or a public IP address. Okay. Private are used for LANs, and even I'll throw in there MANs as well. We went over last week. Public includes what we went over last week, WANs, remember, which is a wide area network, which includes the internet. And so you'll learn again more about that this semester. We just know tonight, IP addresses are made up of 4 octets. Each octet in its rawest form is a binary. And you will do a lab this semester of converting binary to decimal, decimal to binary, and learn how to do that by hand and also by the scientific calculator. And then you'll set up your own private LAN as well, to where you can communicate on the network, the same network. And the only way you can communicate is if you have a unique IP address. So the next one is IP addressing management, and this has to do with not local IP addressing, but global internet IP addressing, like for websites, okay? Like for Google, for Apple, for Rock Valley College. Initially, this group was managed by what's called the IANA, Internet Assigned Numbers Authority, and Al Gore did not work for these folks, by the way. He says he did, but no, he didn't. But in '97, there was 3 registrars called Regional Internet Registries. One was the American Registry for Internet Numbers, ARIN, Asian Pacific Network Information Center, APNIC, and then Réseau IP Européens, RIPE. So there's 397 on IP addressing. Now, since the late 90s, they've all come into what's called the ICANN, Internet Corporation for Assigned Names and Numbers. It is a private nonprofit, remains responsible for IP addressing and domain name management. The IANA performs some system administration for this group, and users and businesses obtain IP addresses from their ISP, but it's managed from the ICANN. They're the ones that manage all the numbers, okay? And so an example would be, GoDaddy is an example. You can register a domain there, right? And then they give you an IP address. And there's tons of other domain registrars out there. That's just one big one that you probably heard of. But regardless of where you don't register a web domain, these folks, the ICANN, are going to be the ones keeping track of these IP addresses. And again, because of the growth of the internet, they were seeing before IP version 6 that probably by 2025 they would be running out of internet addresses for public web servers, or running close to being out. Now with IP version 6, they're talking like, almost 1,000 years out, maybe we'll be getting close. So we're good for a while. Okay. We're good for numbers for a while. In fact, just so you know, not to bore you too much technical stuff, but IP version 6 gives us not just what we have now, which is the 4 octets. It actually includes in there some alphanumeric octets as well included, which gives us a more range of numbers and dynamic range of numbers. They're even talking about eventually having separate IP addressing publicly for emergency folks, like for fire, police, government, military, and totally on a separate IP range, and totally on a separate they call it alphanumeric range than the public will use. And that will actually help with security, because folks in the consumer, or in the consumer realm, won't even be able to talk on the realm for military and governmental, which will be good. It'll help with security, that's for sure. Now, will hackers figure out a way to get around that? Probably so, but there's going to be a little bit to do that, I'm guessing. So OSI model, let's get into that. Basically, it's a model, just like when you hear the word model, you think it's something to kind of model my life after, or model, when you do a model car, I used to do model cars as a kid, build model cars, replica of something else. But also a model can be a standard as well for something. And that's what this one really means more of, as a standard. So it's just an understanding and developing a network computer-to-computer technology, some model to do that. It was developed by ISO in the 80s. It divides a network into 7 different layers: physical, data link, network, transport, session, presentation, and application. The protocol interaction is that the layer directly above and below plays with each other, and they do overlap some. You'll see in a second. The application layer protocols interact with software, and the physical layer protocols interact with hardware like your NIC card, cables, and connectors. So it's a theoretical representation describing a network between 2 nodes. It's hardware and software independent. Nothing you have to download, it's just a model. Every network communication process is represented. And they have what's called PDUs, which is protocol data units. It's a discrete amount of data. It's on the application layer function, and it flows through layers 6, 5, 4, 3, 2, and 1. It's a generalized model and sometimes imperfect. So here's what happens on a OSI model representation. You have 2 nodes, computer A and computer B up there. And you'll notice the 7 layers are exactly identical on both sides. And the way it flows will start up on the left side here, going down. We'll say the application, we'll start at the very top, the application layer. And the application layer is working with software. It's not software, but works with software. Like, say, for instance, Eagle works on Firefox right tonight, maybe, that you're working on. It's a application layer that has conversion stuff in it. So if you're an Eagle and you're on a website and you have to upload something, or you have to log in tonight and put your name in the lab, 3 before I forget, you do that on Eagle, right? As soon as you submit it, it's going to convert that and start going down the path into presentation layer, which is taking that submission you just clicked on Eagle to submit that name and convert it into binary, go to the session layer, transport layer. Now you're getting ready to go onto the network, data link layer, and the physical layer is the actual NIC card of the OSI model. And it's also the one that has the Cat5 cable connected to it. It's the actual physical layer. Flowing down to the next one, it goes up through the next computer, through a physical NIC card, data link layer, network layer, transport. Now it's getting ready to convert the binary system into whatever application it's going to open it up into, which is a web browser. Session layer, presentation layer, then it converts it to the application to see it, and then starts it all over again on the other side. And so that's the flow of OSI. And now this flow it shows you here is exactly, one-to-one, no overlapping, but it doesn't work that way. It is a lot of overlapping sometimes on different processes that you'll learn about this semester. So let's talk about these layer by layer. The top layer, seventh layer of the OSI model is called the application layer. It is not an application, but it does not include application, but it works with functions that application uses. It facilitates communication between software applications and lower level network services. The network interprets the application's request. So an example would be, if it's an FTP client, you're uploading stuff to a web server. It recognizes that request. Port 21 needs to upload some stuff. Network's going to interpret that. Oh, we can't let you into port 21. We blocked it. That's going to happen here in the application layer. Application layer interprets data sent from the network. Software applications negotiate with the application layer, like what formatting should it be? If it's an audio coming in through binary, it's got to convert it from binary into audio. It's a video, it's got to convert it from binary into video. If it's a text message system, like Eagle, basically just plain text coming across, it's converting into binary into text via email from your instructors and from instructors back to you, you back to instructors. Synchronization and other requirements might occur as well. An example of application layer protocol would be HTTP. We actually looked at last hour with my network security guys. This is a protocol where all your web browser sessions happen, okay? Where you visit a website, you click on a link, it's going to use this protocol in that session. And so that's done in an application layer because it's using a web browser to do it. Whether it be IE, Firefox, or Chrome is irrelevant. It's the same protocol on all three browsers, which is HTTP protocol. So we have here an example of a web browser collecting and displaying content. It's requesting content as it clicks on a website link. It gets content, and that content application layer protocol is called HTTP. That's the protocol. So you click on a link, it goes to the web server, it downloads to your browser, and you get to see it, right? Everything's working good. Presentation layer is the next one. So application, now presentation. It's a protocol function. It accepts the application layer data. It formats it. It understands a different application and host. Examples of file types and translation would be GIF, JPEG, TIFF, MPEG, QuickTime, just to name a few. Presentation layer services manages data encryption and decryption. An example protocol would be SSL, Secure Socket Layer, for securing data. An example here with the same information earlier. Example, we have web browser, APIs, your HTTP, and whatever protocol. It detects and indicates that, hey, you're on a banking website. So it's going to be secure. You got an HTTPS, and it's going to notice that. Or, hey, you're on a TLS, which would be basically a security protocol within SSL. That's another wrapper it recognizes. And that's all found on the presentation layer. So the application layer here represented as HTTP. Presentation layer would be the wrapper around that HTTP, which might be a secure socket layer. It might be a TLS, a number of other things. Session layer. This layer is a protocol function of coordinating and maintaining communication between two network nodes. The session layer is a connection for ongoing data exchange between two parties. A connection between remote client and access server, and the connection between the web browser client and the web server. So the session layer keeps things going. It keeps things connected. It's a handshake layer. It's constantly handshaking back and forth. Are you there? Yes, I'm here. Are you there? Yes, I'm here. Are you there? Are you really there? He's just constantly doing that all the time. Are you still logged in? Yes, I'm still logged in. Are you still logged in? Just constant all the time. If it was to talk, that's what it would say. All right, it's just a constant session all the time, seeing if it's connected, seeing if the session layer is still there. The functions of this is keeping it alive and that session link, keeping the communication secure, synchronizing dialogue between two nodes, determining if communication has ended or not, determining where to restart transmission. Example on this one would be, have you ever started downloading a file? It was like really quick, fast, like super, super duper fast. And then within seconds, it's like dirt slow. You ever had that happen before? You're like, what in the world? And then maybe there might be times where literally you went back and it's like it's not even downloading anymore. It's stopped altogether. And then you watch it and it started up again. Okay, this is a protocol that does that. If a download ever does stop because of network congestion or whatever, your Wi-Fi went out for a second and then it comes back, the part that kicks it back up is the session layer. It also terminates communications. So when you log in or log out, this is a layer that flushes that out completely and notifies all other systems that you've logged out. It also sets terms of communication as well. Like maybe it could be the network set a protocol that you can't log in from midnight to 6 a.m. This is a session layer. The session layer would be the one that it would talk to do that. It also identifies session participants. So live chat modules, Facebook, Twitter, heavily uses a session layer all the time, nonstop. So an example here, we have the cloud, which is the internet, a couple servers, server A and B, and then we got two internet phones, voice over IP phones, that every business pretty much has today. And notice is doing what I said earlier, requesting a call, okay to go ahead, yeah, still there, still here, end call, okay. All right. Constantly going on all the time in the session protocol. And so we just know it works and we know it or it doesn't work, right? Your cell phone works or it doesn't work. There's no in between. This is the protocol that does it. Even on cell phone would be a session protocol. On networks, same thing, session protocol. Determining whether or not you're still there and constantly determining if you're connected, constantly determining if that security is still there. And if it's not, it'll disconnect. Or if it's stopped a session for a time for whatever reason, it'll reconnect. And then finally end the session. The transport layer accepts data from the session. It manages the end-to-end data delivery. Data flow is handled here. This is connection-oriented protocols in this one. And what it does on this one is establishes a connection before transmitting data. An example would be a handshake I talked about earlier. Anybody remember the days of dial-up? One person. Okay, there's a few of you. Okay. Okay, what happened when you first logged into a dial-up connection? What did you hear? A whole bunch of tones, right? And then shriek noises. At the very end, right before it connected, it was yeah, that's it right there. Thank you, appreciate that. And I didn't ask him to do that before class. It was awesome. Yeah, that shrieking noise, that's what that is. It's a protocol handshake that's saying, okay, we're now connected. And then once that shriek ended, whoo, you were connected. You know, it was a good sound. It was kind of like, oh, and then, oh, okay, good, I'm connected. Well, the example of the three-way handshake is this: synchronization, acknowledgement, and then acknowledgement. That's what that shriek sound is doing. It's synchronization, acknowledgement, and then finally acknowledgement, and the shriek ends. Now, your NIC cards, by the way, have this on the little lights on the back of it. The little green light, yellow lights, red lights are showing you all the time that handshake occurring. You just don't hear it anymore. Thank God, right? Except for when we need a sound clip, we need it. Thank you for that. I'll pay at the end of class for that one. That's awesome. Next is a checksum in the transport layer. That's a unique character string that what it does is basically whatever I sent to the person I'm sending it to, a checksum has to match on both sides. Okay. It allows a receiving node to determine if the arriving data matches the string data, the sent data. And it does also have connectionless, but also connection and connectionless both. It does not establish connection with another node before transmitting data. It does not check for data integrity on connectionless protocols. And it's faster than connection oriented because there's no rules around it. All right. And so the transport layer, what happens is it does a handshake, it gets connected with those protocols, those strict protocols. Once a connection's there, then it lifts protocols sometimes for data flow. An example would be the download thing I mentioned earlier. You log into a website to download a file. When you're logging in, it's going through some connection type application stuff, authentication, handshaking. Once that's secure and found, then it lifts the protocols to allow more full reign of data just to flow at a faster rate. And then what it does is every once in a while it just checks to see, okay, are you still connected? Are you still connected? But it's not in this, it's in the session. Not in this one, but in the session. The transport layer is just transporting stuff, is all it's doing. The transport layer also does what's called segmentation. I like to represent this one as a caboose. If anybody has a train. No, okay. All right, well, I'll draw like I usually do. My beautiful drawing here of my grandson that loves trains is a representation of what we're getting ready to talk about. We'll say we have a 6 meg data packet and it's going across the network. What your network does in this layer is breaks apart that 6 meg into 3 separate 2 meg packets, all right? So it can go across easier, more efficiently, without really using much bandwidth. And by the way, in this layer, it's also where a lot of times I talked about earlier, when you click on a link and it downloads quickly at first, and then it slows down. What's happening is, in this layer, it's realizing, okay, I can see now what your connection is here. It's not the greatest. I'm going to start slowing it down. And not only that, it sees all the other connections at the time connected to that same file, maybe that people are downloading around the world. And it says, in order for everybody to get this file successfully, we're going to throttle everybody's download to whatever speed. And that's also the reason why you see it slow down from a really quick download to really slow download. And sometimes those download speeds aren't much faster than dial-up at times. You know, might get down to 34K or 56K or whatever the case may be, and then bump up to 2 or 3 megs a minute, and then back down to 56K. And it's just, again, who's hitting at the time, and also your internet service at the time could be it as well. But that happens here in the transport. But what it does first is breaks up when it sees what your connection speed is, sees what that's in the session layer, what's going on. Then it begins to break it up in bite-sized packets called segmentation. It breaks it up, large data, into smaller cabooses, and then it increases the data transmission efficiency on network because instead of a 6 meg packet going across, now we just have 3 2 meg. And I might even break it up further than that if need be. Whatever your data can handle, whatever your network can handle at the time. So the next thing is called a maximum transmission unit, which is the largest data unit that can be carried upon the network. The Ethernet default is 1500 bytes, is a default on an Ethernet network like ours. And the discovery routine is used to determine whatever the maximum transmission unit is at that time on your network. And then it breaks it up accordingly on these cabooses I drew up here on the board. Then what the beauty of it is, it reassembles it. So it breaks it up. Then when it gets to the user, we'll say this is the source, this is the destination. When it gets to the user, it reassembles it back into that nice 6 meg file for the user to open. You don't know that, and I don't know that. It just happens, right? We got the file, it works. Hey, I don't care if you have to split up into 5,000 million pieces. As long as I get it, I don't care, right? But I think it's pretty awesome that it can do that and that it does that seamlessly. And in the video tonight, it actually shows in one part of the video where an IP packet fails to be delivered, and the router through IP just tells the destination or the source, hey, I need another IP sent, and it resends a new one. That's all done in this area here. Sequencing identifies the segments belonging to the same group and subdivides it. So in this transport layer, say it gets to this level, and for some reason, one of these fails coming across. What's going to happen is IP is going to go back to this computer through IP protocol and say, okay, we need another one. It's going to resend that one that was lost and then repackage it to successfully come in. But again, you don't know that, and I don't know that, but it's happening that behind the scenes. And in fact, you might have seen this happen when you downloaded files. It gets to 100%, you're like, okay, it's 100%. Why? Okay, it's 100%. What's happening? It's 100%, right? Is it done yet? It says 100% now for like a minute. Have you ever had that happen when you download files? What's happening is this right here. A lot of times it's reassembling, putting those back into place, and there might be one that it has to go back and get and bring back again because it failed coming in, and that can happen. So we have here an example, a sender to receiver. On the sender, sends a long message and puts it in a caboose, multiple cabooses, one letter character per caboose, sends it across the network, goes to the transport layer, reassembles it back for the user to see. Crude example, but very realistic, and that's what happens on a very granular level. And so it's happening all the time, every single moment on the network, and we don't even see it. Here's what a packet looks like on transmission, a log file looks like, and basically it's the source port, which is generally going to be port 80 through the internet, destination port, sequencing number, acknowledgement number, the header packet, and then these acknowledgement flags are, like, say for instance, there might be some congestion that have happened. It'll notice that in here, and maybe at times stop something for a while, for a few milliseconds, and then pick it up again. There are a couple things you can set on the switch side to make a packet or a certain computer, like a server, urgent. All the requests that comes from this server to anybody in the network is urgent all the time. And it gets priority. You can prioritize things as well. Then the network layer. This translates a network address into a physical counterpart. So it decides how to route data from the sender to receiver. The addressing in this is a system for assigning a unique identification number to a network device. Now this is different than an IP address. A network address is totally different. A network address is assigned to that device for that type of communication and for a period of time. And network addresses, by the way, can change, all right? Just like IP addresses can change. And the types of addresses are logical or virtual addressing. And so logical addressing would be something to where a network admin has set into place a range of network addresses available to its hardware devices. Virtual addresses would be such things like virtual operating system, virtual servers needing a virtual network address to function. And then a physical address would be something like some of your network devices do have hard-coded in the device a network address that will be hard-coded in the device, kind of like a NIC card has a hard-coded MAC address in it. So here's an example of a network address, a 10.34.99.12, physical address, that number there. Factors using to determine what path is taken on the network in the network layer will be what priority it's been given by the network admin in managing the switches and routers. Network congestion. Hey, what time of day is it? Is it 9 o'clock in the morning? Is it noon? Pretty congested in most businesses, right? Quality of service. That refers to your hardware. That refers to your cabling. How good a quality is it? If it's low quality, or if it's they're really aged and out of sync, or maybe the settings aren't correct, it can cause a problem. And also factor of cost of alternative routes. What that means is if it hits a switch that's failing or a router that's failing, and it can actually be smart enough, your NIC cards are smart enough to determine where else to take it. All right. And routers belong to this network layer. Routers belong to this network layer, and they work in tandem with your NIC cards and other switches on your network. And routers, by the way, are actually called as a smart device, an intelligent device, and they determine any moment's notice the best way to get that data there. Maybe not the fastest, but it's the best way. So common network layer protocol would be IP, and then fragmentation is much like here we did with the data, but it's fragmentation with the network traffic. And it's going to basically break it up and segment it back to work together on the network. Segmentation is preferred over fragmentation for greater network efficiency. Here's a screenshot of the only thing you need to note on this screen is the flag that says don't fragment or more fragment. Don't fragment means don't fragment it. You're going to just use a hard-coded address. You're not going to fragment it. Whatever the packet size is, that's what's going to go over. Time to live is the other one. That's 64 hops. What that means is from 64 devices, it's going to decrement every time it hits a device by 1. When it gets to the last one, it's over. It's dead. That network, and they'll have to refresh a new one. Data link layer. This function here divides the data received into distinct frames for transmission into the physical layer, almost into the NIC card. So in this one, the frames are the package itself moving the data. It's the data payload. It's the movie, it's the raw data, it's the film, it's the audio, whatever it is that's being brought across. It has the sender's and receiver's data address, error checking's in here, control information's in here. Possible communication mishap can occur when not all information is received. And it will do the same thing I mentioned here. It'll go back and get the packet that was missing, correct it, the checksum. Possible glut of communication request could also be caused by a NIC, allowing a NIC to process data without error. Could be that, meaning your NIC cards by nature let anything come in and anything go out. Okay, and that can cause some overflow at times. But your network is smart enough. Your routers are smart enough to control all of that, by the way. Then there's two data link layers, sublayers. One is called the LLC, which is logical link sublayer, and one is called the MAC layer, the media access control layer. The MAC one manages all access to the physical medium itself. And so this one is appended to the physical destination of the computer. And the MAC address is on the NIC card itself. By factory, just like in a car where they put a VIN number, in factory, they put a hard-coded MAC address on every NIC card. Okay? Those can be hacked, those can be cloned, but they are there. Just like a car's VIN number could be hacked as well, and somebody could go in and file it off and put another one on it. You know, that can happen. But by factory, they're given a separate MAC address, and it's appended in the actual network protocol on the data link layer. The physical address is a fixed number associated with each device's network interface in the data link layer. So we have here in the data link layer the logical link layer, which is common interface, reliability, flow control. Then the media access control, which is the actual getting ready to go into the actual NIC card and the components of that. So here we have a screenshot of something you might have seen before, or maybe not. This is a wireless NIC card, and they work well in areas of your house, maybe your building where you don't want to run Cat5 cable. You can buy a wireless NIC, put it in the computer, and you don't have to run cable. And you'll notice it has circled there in red the MAC address. And the MAC address is made up of one part manufacturing, has their own little code for the MAC address, and then one part random number for that or not random number, unique number, sequencing number for that manufacturer. So the functions of the protocols on the physical layer are accepting frames from the data link that we just came from, generating signals as changes in voltage in the NIC card. And by the way, there is voltage in the NIC card coming out. Most students don't know this, but you can buy what's called power over NIC. And what it is these two, looks like big plug-ins, right? Big plugs. You plug one in the wall, put your NIC Cat5 cable into it, plug it in your computer, go downstairs, put another one in the wall, plug in your Cat5 cable, plug in your computer, boom, you got internet, you got network. You're working together through your power in your house. And the last time I checked, they're about 70 bucks for a 2-unit piece, which again is much nicer than running Cat5 cable throughout your house. And it's power over Ethernet. And it's using your power in your house to transform it or translate it and to bring it over. So there is some voltage, and here in the physical layer, that's where it's managed. Copper transmission medium, which is Cat5. Signals are issued as voltage. Fiber optics, another transmission medium. Signals are issued via light pulses. And then wireless transmission medium, signals are issued as electromagnetic waves, which can get interference. You'll learn this semester from your garage door opener, your microwave, your wireless surround sound in your house, just to name a couple things that can give interference. Physical layer is responsible when receiving data to detect and to accept signals. They pass on data link layer. They set the data transmission rate. They monitor data error that are on the network physical layer. And devices operating at the physical layer, hubs and repeaters. Now, hubs are a word, actually, one of these days will probably be out of the books, but it's still there. Hubs are basically, and we use some this semester, they're the dummy routers. They're just dumb. They're just first come, first serve. There's no rules in a hub. You know, you can still buy hubs though. And they're just not smart. They're just first come, first serve. They usually have 4 to 6 ports, and you can share computers' data flow to them. But repeaters would be, an example on repeaters would be, they can be used for wired or wireless. On the wired side, you can have repeaters that just go from a switch to switch and a repeater in the middle to just, because Cat5 cable is only supposed to go about 150 feet, 200 feet max. And so if you had, like, say, a 400 feet range and you didn't want to buy another switch because they're more expensive, you could buy a repeater to go in between the 2 switches. Wi-Fi also has repeaters. You can buy a repeater box. D-Link has them. Linksys has them. They're a little bit cheaper than a Wi-Fi router, and they just repeat your signal. Okay, they make it go further in your house or in your place of business. NIC operates both on the physical and the data link layer, and here's one of the examples I talked about earlier where the overlapping occurs. And NIC is one of those overlapping. It occurs all the time on the data link and physical layer both. So, applying the OSI, going over one last time here, starting at the top, the application layer provides an interface between software and application and network interpreting application requests and requirements. Presentation layer allows host and application to use a common language before data formatting, encryption, and compression. Session layer establishes, maintains, and terminates user connections. Transport layer ensures accurate delivery of data through flow control, segmentation, reassembly, error correction, and acknowledgement. Network layer establishes network connections, translates network addresses into physical counterparts, and determines routing. Data link layer packages data into frames appropriate to the network transmission method. Might be Cat5, wireless, fiber. And then physical layer manages signal to and from the physical network connection. And this is the one that includes your Cat5 cable and your NIC card in this one. So I want to skip this one. I want to get to another thing I was wanting to cover here. Oh, this right here, Wi-Fi, sorry. This right here. I'm going to end on this. Here is some protocols on Wi-Fi standards that you've heard of some of these things. 802.11 you might have heard of. How many's heard of that before on wireless? Okay. Some of the other ones you might not have heard of, so I thought we'd end on this one before we go to the video. So 802.1 one of the first standards in Wi-Fi. Bridging and management dealt with routing, bridging, and network communication. Then 802.2 was logical link control. This dealt with airflow control over data frames. Then 802.3 Ethernet. This is all forms of Ethernet medium interfaces. So this is your hardwire standard. Token ring, 802.5. All forms of token ring media interfaces. I remember we talked about token ring last week, how some of your PCs and token ring will actually have 2 NIC cards, one for in, one for out. And wireless LANs. You guys have heard of this before. Standards for wireless networking for many different broadcast frequencies and usual or usage techniques. The next ones here you probably haven't heard of. 802.15, wireless PANs. Coexistence of wireless personal area networks with other devices and unlicensed frequency bands. This would actually even fall into place of your mobile phones being able to share Wi-Fi hotspots. That would be a PAN. Bluetooth, PAN. All right, so those are 2 common ones you've heard of. Broadless wireless bands. This is atmospheric interface related functions with broadband wireless connectivity known as WiMAX. Clear Communications is one company here nearby. Schaumburg has them, where basically you can buy into service for $40 a month and get internet within a 30-35 mile radius wherever from the antenna with the right software, the right hardware. We're pretty good. I mean, it'd be great if we had that here one day. If we will. We're working on it, I know. I've talked to the guys there and they're working on getting it up here. 802.17, resilient package rings, access method, physical layer, specification, management of what's called sonnets, which is basically large metropolitan rings to put cities to cities together, metropolitan areas. Then 802.20, mobile broadband wireless, packet handling and specification for multi-vendor, multi-high speed, nickname mobile WiMAX. AT&T is looking into this, by the way. Be one of the first ones out, mobile WiMAX provider. And then 802.22, and by the way, I'll just stop on the 802.20. You might have heard of this one. It's actually called the Home Box. It's a little box. It's kind of, you can buy these now like the Verizon, you know, the little boxes to share internet, but they're for wider ranges. The Wi-Fi Max is for wider ranges, the mobile WiMAX, to where literally like AT&T is going to be creating to where they can have these drops around cell towers to where you can buy a service, and it will basically be in competition with WiMAX, which is basically the backbone of that is cable internet. Mobile WiMAX backbone would be cellular. Which really, if you think about it, for mobile users, the WiMAX is probably going to be a more feasible way to go because it's going to be everywhere. It is everywhere. Mobile towers are. And so, anyway, 802.20, 802.22, wireless regional area network is a standard of wireless broadcast networks to operate on the UHF, VHF frequency, formerly known as your TV channels. So, over the air, right? How many saw this over the air? I've got it. I got over the air. I love it. Yeah, I dropped a Comcast 2 years ago. I never looked back. And so, but anyway, that's the different standards for 802.11.12 all the way up to 22. All right, ready for video? Okay, I'm going to turn off the lights if you guys promise not to go to sleep. All right, remember it's 13 minutes. Pretty painless. Hopefully you enjoy it. No, you will. It's a good video. And again, it talks about pretend you're in front of a computer. You're not. You are in front of a computer. You don't pretend. And you want to click on the link. This video is going to show what happens when you do that. Okay. Scroll back.